All right, let's finish up this series on classical groups. We have gotten pretty far. What we have done is we have shown that the metric for any metric space, so our metric space is always some vector space V. We know bases can be applied. It's got n dimensions. Better make my n a little more aggressive. And it has a metric of sorts, right? Some type of metric is applied. That's what makes it a metric space. And it's over a field. And we're talking about the real field, the complex numbers. We're always talking about real and complex numbers. The question is, do we want F to include the quaternions or not? And for the purposes of our analysis of the classical group, we are going to not include the quaternions right now, and then we'll show you how we handle the quaternions at the end of the lecture. So this will truly be a field. By the way, I read yet another paper the other day that identified the quaternions as a skew field, right? Making it very clear that almost all of the important results are dependent on the quaternions being a division algebra, not necessarily a full-fledged commutative field. Anyway, I'm a little defensive about that, but I don't need to be, because that's what Gilmore does. Gilmore likes to think of it as a field. Okay, so we now know how to interpret this inner product as a matrix, right? And we've gone through that work. And as I pointed out, for those of you who took the What is a Tensor lecture, where I warned you about doing that, now I'm saying, okay, it's all right as long as we understand how everything works. And we know that given that we have this vector space, we have the set of all linear transformations of the basis, right? So we have the set of sort of all basis changes, right? And we're going to interpret this as the set of all possible basis transformations for an n-dimensional vector space over the real or the complex numbers. So I'm writing it this way to show that we know this is a group under matrix multiplication. Well, actually, so the way I've written it here, the general linear group F and N, sometimes that's understood to be the abstract group, right? This is the abstract group of linear transformations of the vector space. And some books will then say, yeah, in order to understand this as a matrix, we got to think of the matrix group of n dimensions over a field. And these are the matrices, right? And it turns out, of course, this is isomorphic. So once you have things that are isomorphic, you stop worrying about, these distinctions. So and certainly Gilmore doesn't worry about the distinctions. So, well, he will in the next chapter. But for now, we're going to consider this the matrix group under matrix multiplication for basis transformations of an n-dimensional vector space, where n is a finite number, right? All these classical groups were treating n as a finite number. So so this is a very big group. We then learned that we can make this group a little smaller by creating this special linear group over the field in n dimensions, and those are the volume preserving groups. And we showed that the volume preserving groups are such that their determinant is equal to 1. So if say A is an element of that group, then the determinant of A will equal 1. And there are a few caveats on that, right? Because there are sometimes if A is a complex group, sometimes it's the modulus of the determinant that equals 1. And it is also possible to have some determinants that equal -1, but those are not the special linear ones. Those are the opposites of the special linear ones. So anyway, let me not worry about that, right? Anyway, the point is that these are the volume preserving groups. So we have the total, all possible basis transformations, and then all possible basis transformations that preserve the volume, which is a subgroup, meaning the product of any two volume preserving basis transformations is also a volume preserving basis transformation. All right, so with that, now let's just consider all the elements of the general linear group that preserve these matrix elements, which is another way of saying A, let's see, for sesquilinear matrices, it was A adjoint, right, this little t, G, A equals G, right? So, let's see, so we're looking for all of these guys. Now, of course, all of the matrices that preserve G and preserve each element by element of G. So when I say preserve G, I mean that Gij transforms to G hat Ij, which equals Gij, right? Each matrix element literally doesn't change under this isometry transformation. And then what we showed is, well, wait a minute, obviously selecting the A's for which this is true out of the general linear group, when we choose all of the different basis transformations for which this is true, for which this stuff is true, I guess I should put a G hat there, right? This is sort of the transformation rule. The new matrix, is the old matrix transformed by A, and this is what we're after, that the matrix elements of the new matrix equal the matrix elements of the old matrix. That is what causes A to be an isometry transformation of G. The point is that obviously choosing all of the A's for which this is true for a given vector space depends highly on what this inner product is, right? So if the inner product Gij is basis vector Ei, inner product basis vector Ej, we need to understand what that guy is in detail, its properties, and once we know its properties, we can then start hunting for the A's. And then in the last lecture, what we did is we showed that for at least in one case, we can actually really get to the bottom of what Gij is. In particular, for a bilinear, symmetric, non-degenerate metric, we know that any such metric, bilinear, symmetric, non-degenerate metric, we know that that can always end up is one basis transformation away. So in other words, we have a bilinear, symmetric, non-degenerate metric, and then we calculate Ei, Ej for whatever basis we happen to be in, right? And that is the matrix of this particular bilinear, symmetric, non-degenerate metric. We just do this calculation for each of the basis vectors, and we get each of these matrix elements. But we know that we can find a basis transformation that will always put this guy into the form where there's ones along the diagonal and negative ones along the diagonal, right? And zeros everywhere else, right? And that basis transformation is just your typical basis transformation of the underlying vector space. And that typical basis transformation, if you choose it correctly, we've proven that you can always find it so that Gij takes this form. Well, that's pretty interesting. It turns out, and we're not going to prove it, but that is also true for sesquilinear Hermitian non-degenerate metrics, where Hermitian is where we replace the word symmetric with Hermitian. But Hermitian is a form of symmetry. It's just the symmetry that reads VW equals WV with the one automorphism of the complex numbers that we actually know about, which is complex conjugation. This is called Hermitian symmetry. And if we have sesquilinear Hermitian non-degenerate metrics, we can also do the same thing, right? And so basically, if we have a sesquilinear Hermitian non-degenerate metric for where the field is the real numbers, then these two are the same anyway, right? Because sesquilinear becomes irrelevant for R, it just becomes bilinear in a real number, and Hermitian symmetry doesn't mean anything because the complex conjugation goes away. So this is actually like for real numbers, this and this are the same. For complex numbers, it's not. This is actually different from the idea of a bilinear symmetric non-degenerate metric in the complex numbers. But we also saw that if you really had that for complex numbers, all these things would be 1, right? These negative ones come up from the fact that you might have square roots of negative numbers that you have to sort of deal with in your analysis of normalizing things. But if you have complex numbers, you can take the square root of anything. So these will all end up being ones if this is a bilinear symmetric non-degenerate matrix over the complex numbers. But over the real numbers, you get these ones and minus ones. Anyway, so we now know that sesquilinear Hermitian non-degenerate metrics, which is really what we're going to talk about more. We're going to let this sort of fade away because this is the one that has every... First of all, this for reals, it's the same. And for complex, you don't really deal with these in the complex case. You deal with these. So we know that we can always create a matrix in that form, and so now we ask ourselves, can we find basis now once we've done it? Okay, so that's important. There's two basis transformations I'm talking about here. The first basis transformation is just whatever arbitrary basis you have for your initial vector space, right? You have some basis for this initial vector space. And in that basis, you cast the matrix form for the metric, right? You find Gij. And you say, wait a minute, I just did that, and it didn't look like this, right? Well, that stinks, because I know it should be nice and easy and look like that. So now you kind of have a preference for what basis you want your vector space to be in, because once you have the inner product, why not make the inner product as simple as possible? So now you're going to execute a basis transformation to put the inner product in this form. Okay, now that is arbitrary basis transformation because you don't know what you started with. We're assuming you start with any basis, right? So taking any basis and putting it in this form, we can't characterize that. But once we're in this form, now we have a vector space with a specific basis and the metric is in this form. And now we can look for all of the isometries of this particular form. And that would end up being, the typical. Now we look for a basis transformation A, such that A adjoint G A equals G, right? Literally, we don't even need to put a hat there because we're the matrix elements are identical. So then those isometries, we gather them all together into a set, right? And gather them all into a set, and obviously, yeah. So we gather them all into a set, and those isometries and anything that's similar to them, meaning any subsequent any subsequent similarity transformation acting on those matrices will then all be part of the isometry group. So that's what we're after. We're looking for these sets. Now, the point is studying and gathering and doing a full analysis of all the isometry groups and what those matrices look like that preserve these metrics. That's a different subject. That's called representation theory. And inevitably, we will have to talk about a big chunk of representation theory in our work studying Lie groups and Lie algebras. But we're not going to do it now. I'm just going to name the different groups that exist, because that's what Gilmore does at this stage. He just says they exist, and here's what we can determine about them. And the first thing he points out is kind of this obvious fact. Well, he says, wait a minute, if I can take any sesquilinear Hermitian non-degenerate metric, and if I can put it in this form, that's tantamount to saying I can count how many different possible sesquilinear Hermitian non-degenerate metrics there are. Right? For example, in this case, this is a 6-dimensional vector space, right? Here I have 3 1s and 3 minus 1s. Whoops. What happened to that minus 1 here? There should be a minus 1 there. Well, wait a minute. I can also have a minus 1 there. So there's another, and that's different. That's not the same. That's a totally different metric. And then I could have a minus 1 there, and that's a different metric. Or, likewise, I could have these being plus and only 1 minus 1, right? So I can actually count the different possible sesquilinear Hermitian non-degenerate metrics, right? And it turns out for any dimension n, for any vector space of dimension n, there will be n plus 1 different possible sesquilinear Hermitian non-degenerate metrics. So that's kind of interesting, is this process has allowed us to count the different possible ones of those. Okay, so now Gilmore talks about one other type of metric, right? He's really big on this, right? And this by inclusion, but he's really big also on another type of metric. He's very interested in bilinear anti-symmetric metrics, and he doesn't demonstrate it in the book, but the proof is not totally dissimilar from the one we did previously. But for what it's worth, those metrics for those vector spaces can canonically be put into this form, where you have -1. First of all, the only thing that's occupied is the so-called minor diagonal of the matrix, of the matrix elements. Only the minor diagonal are non-zero. And you have an equal number of -1s and +1s on the minor diagonal. So this number here, that if there's p of those, then there's p of those. Now back here, remember, if you have p1s, you can have q minus 1s, and p plus q has to equal n. But in this case, n has to equal 2p, right? So the key is that a bilinear antisymmetric metric can only exist in even dimensions of space, And if you want to see how that flushes out, well, it's all about the asymmetry, right? So here VW equals minus WV. And what's really important is that implies that VV equals 0, right? VV equals 0. And these two things, when you run them through the proofs of how can you make a nice canonical metric matrix representation, you end up with this implication that n has to be even. I always thought that's cool. I like things. I'm fascinated by things that depend on the dimensionality of these vector spaces. It's just this really fun intersection between number theory, and it's kind of neat because if you really study this stuff, you discover that n equals 4 is like a really unusual, problematic dimensionality. Sometimes n equals 3 is a big problem. N equals 2 and 1 are usually not so bad, and then 5 and higher aren't so bad. But then there'd be like weird things that happen in strange numbers of dimensions. I wish I understood it all a lot better. I've reviewed a lot of it, but it's pretty esoteric. It's a bit out there. But this one is pretty accessible. Bilinear antisymmetric metrics, even dimensions. And you get this canonical form. But now you can see that this canonical form there's really only one for each even dimension space, right? There's only one bilinear antisymmetric metric. It's bilinear too, by the way. Okay, so those are the two types of metrics that mean the most to us. Well, there's actually three. So there's three different types of metrics that matter to us. And the reason these matter is these are the kinds we can put into a canonical form. So they're kind of special. And turns out all of nice physical theories seem to use these guys. This, of course, are the type of metrics that you find in quantum mechanics. And these guys you actually find in classical mechanics a lot. And these guys also show up in various places. But this is quantum mechanics. This is really advanced classical mechanics. But they're all important. They're all important. And mathematically they're important because they sort of stand out because they're easy to identify. And the symmetry properties are very just commonplace. So the point is we now are looking for isometry groups, which is we're now looking for the set of elements that are part of the general linear group of some field f in n dimensions, such that, and then I guess we would write A transpose G A equals G, something like that, right? Preserves the bilinear symmetric metric. And likewise for the sesquilinear Hermitian metric, is the set of all members of the general linear group where the A adjoint GA equals G. Remember, this is how you do a basis transformation of the metric, right? Which is a little different than the basis transformation of an arbitrary linear transformation. Remember, we showed that the interpretation of the metric as a matrix requires this process for a basis transformation A, where A times some basis E gives you E hat, right? The new basis, right? And whether or not you get when you take this process and you study how it transforms a metric, you get the adjoint operator, which would be A conjugate transpose. If you're dealing with a sesquilinear matrix, a sesquilinear metric, or you just get A transpose GA, like I wrote here, if you're dealing with a bilinear matrix. So you have two different ways of transforming the metric depending on whether or not the metric is sesquilinear or bilinear. But the point is, once you do this process, this is how you transform the metric. It's not how you transform an arbitrary linear transformation, though. We showed that those are different. The matrices that are meant to be arbitrary linear transformations transform with similarity transformations. Anyway, the point is this set of all these A's will be an isometry, which means it's a group in its own right, and it preserves the metric for bilinear symmetric metrics. Now, we know that for bilinear symmetric metrics, we can define each one in terms of how many positive numbers and how many negative numbers fall in the diagonal. So the name of the set that preserves those metrics that have P positives and Q negatives on the diagonal, that's written this way. It's written as OPQ. And remember, P plus Q must always equal N, the total dimensionality. And this is called the orthogonal group. This is called the orthogonal group PQ. And then when we go to sesquilinear Hermitian, by the way, Gilmore doesn't use the word Hermitian in his book, but that's what he means, right? I put it in there because almost every other book uses it. I don't quite know why he doesn't, or he didn't in this chapter. But the set of all basis transformations that preserve a sesquilinear Hermitian G, right? That is called the unitary group. The unitary group is given by UPQ. And then the last one, it's still bilinear. So if I wrote it down, it would look just like this. But the point is, G has to be anti-symmetric. That is called the symplectic group. I should write that down. The symplectic group of 2n dimensions. So the dimensionality here is 2n, not n. The dimensionality is 2n, but n is sort of half the dimensionality. By the way, I didn't indicate the underlying field in this notation, but you could do that. Gilmore does it with a semicolon separating out the field. So this could be real or complex, real or complex, real or complex. But there's no PQ here, obviously, because you don't have that PQ structure. Now, sometimes Q is 0, and when Q is 0, you would just write O, N, F. And if you know what field you're dealing with, you just write O, N. Likewise, U, N, right? And likewise, SP, 2N, if you know what field's going on, right? So these are the groups that are the isometry groups, and they're all classical groups. Those are some of the classical groups. Now, in addition to those three groups, you can also take, so these are all subsets of the general linear group over a field F in n dimensions, or do I usually write that the other way around? In n dimensions over a field F. These guys here are subsets of this, but you could also take them as subsets of the special linear group in n dimensions over F, right? You could take them as a subset of this group. So as a subset of this group, these would all be, well, okay, let me make it clear. The way I've written them here, O, U, and SP, they are definitely meant to be subsets of the general linear group. On the other hand, I can look at these guys and make them even smaller by insisting that they're also members of this group. In other words, I want the intersection of O, P, Q. I'll drop the field. Intersection S, L, N, F, right? Where obviously P plus Q must equal N, right? So I take the isometry group. There's two different isometry groups at work here, right? There's the special linear group, so these are volume preserving, and these are metric preserving. So some of the metric preserving basis transformations are also volume preserving, and some of the volume preservings are also metric preserving, and so there's an intersection here, and that intersection is called the special orthogonal group PQ. They're volume preserving and metric preserving, right? And they get this S put in front of them, right? Just like that. And yeah, it is not, I know that SSP for the special symplectic group, I've seen that. I've actually seen that written, and I'm pretty sure Gilmore does that. Yeah. So SSP would be the volume preserving symplectic groups. And of course, these are the ones we see a lot about in quantum mechanics. SU2, right? SO3. It turns out that there's a nice relationship between those two that we'll study. I think if we keep proceeding through Gilmore, we're going to hit that one and cover it in great detail. But that's the origin of these groups. They are volume preserving and metric preserving, and they're different, and we count each one up as being different. Now, Gilmore kind of digs into this a little bit more, and he points out that there's other intersections that we could be interested in. He basically points out that if you have a unitary group where P is 2 times, and he writes it as n plus, and you have an even number in the n minus slot, right? You could also have a symplectic group that you could have a symplectic group that has 2n, right? Remember, where n plus n minus, let's see, 2n plus 2n minus would have to equal 2n, right? So you can have a unitary group with 2n plus and 2n, basically an even value for P and an even value for Q. And then you could have a symplectic group where 2n equals P plus Q, right? And he points out that it turns out that some of these guys will also be, some of these metric preserving basis changes will also preserve a symplectic metric of 2n dimensions. So there are elements in this that will preserve two different metrics. It will preserve the sesquilinear Hermitian metrics of 2n plus and 2n minus, but it will also preserve the anti-symmetric bilinear case of 2n at the same time. Therefore, there's an intersection between these two that's not equal to 0, and in fact, that intersection is called the unitary symplectic group 2n plus 2n minus. So there's another classical group called the unitary symplectic group. On top of that, Gilmore lets us know without proof, because all these things are kind of like esoteric. It's fascinating to prove them, but right now there's probably more important things to do. But he shows that this is isomorphic to the unitary group of n plus and n minus without the 2. So it's half of those dimensions, but of the quaternions, right? In this case, this is implied to be complex, right? But this would be of the quaternion. So the unitary quaternion group, n plus n minus, where I've been using P and Q here before, is equal to the unitary symplectic group of the complex numbers. And this is an isomorphism, which means you can map between this group here and this group here, and you can preserve all the group operations, and it's 1 to 1, meaning so it's a faithful mapping. It's an isomorphic mapping. So that's kind of interesting. So this quaternionic classical group is isomorphic to this intersection between the unitary group, a complex unitary group, and a symplectic group. But these isomorphisms are actually somewhat important, and he points out a bunch of these different isomorphisms toward the end of the chapter. So now, to end this, we will review the table produced in Gilmore at the end, kind of summarizing all this. You have two different types of metrics, symmetric and anti-symmetric, and those two different types of metric can be further divided into bilinear and sesquilinear. It's hard to determine which is the more priority or important property. These are all, basically there's four different types of metrics: symmetric bilinear, symmetric sesquilinear, anti-symmetric bilinear, and anti-symmetric sesquilinear. Symmetric sesquilinear, by the way, is Hermitian symmetry. Symmetric bilinear, is just straight up symmetric. Anyway, the implication here is if you have a bilinear metric, you're dealing with Gij, the metric element, equals Gji, right? It's just straight up symmetric metric. Anti-symmetric, you're dealing with a metric that has Gij, the metric element equals minus Gji. And for sesquilinear, you have Gij equals Gji, but with the complex conjugation. Gilmore uses a star for complex conjugation. Other books use a star for full-on Hermitian conjugation, or Hermitian meaning transpose and complex conjugation. And if those books would typically put a bar over it. I use the bar. The bar is my thing, and I'm going to diverge from Gilmore by putting a bar for Hermitian conjugacy. All right, so now we just break this up, and we know that everything in this box here is orthogonal. These are called the orthogonal, this is the orthogonal groups, and they are all given as O, and then there's, I called it PQ, but let's go to Gilmore's notation. N plus positive entries on the diagonal, N minus negative entries on the diagonal for some field F. And Gilmore allows F to include the quaternion. So there is an orthogonal N plus N minus group for the reals, for the complex numbers, and for the quaternions. Likewise, for the sesquilinear groups, they are unitary. They're called the unitary groups, and they're given by U, N plus, N minus, and they are and the ones we are focusing on are obviously the complex numbers, right? Doesn't really make much sense to have over the reals. But you can also have the unitary group N plus, N minus over the quaternions. And we just mentioned that that is equal to the unitary symplectic group of 2n, preserving 2n plus 2n minus, right? So the quaternion, so in other words, the quaternionic unitary group is actually isomorphic to the unitary symplectic group of 2n plus and 2n minus. Kind of cool. But anyway, that's the unitary group. And conjugation in the unitary group is, we did that when we studied quaternions. We know how to do the conjugation of the quaternions. And for the anti-symmetric group, there is nothing here, right? This is an empty spot. There's no sesquilinear anti-symmetric. It's only bilinear anti-symmetric, and those are the symplectics, the symplectic group, which I've already really referenced here, right? Unitary symplectic when we talked about this intersection, right? And this becomes the symplectic group, 2n dimensions over the field. And yes, there is one for the quaternions as well. So now this gives us a handle on the groups we're dealing with. For those instances where we're dealing with, this is where they're all drawn out of the general linear group. If we draw them out of the special linear group, we put an S in front of everything, right? We put an S there. And that's, but those all count as classical groups too. Now, there are a few more that really have to do with the quaternions a little bit. I don't think we're going to get into that now, and it's not that important for the rest of the work that we're going to do. But these are the classical groups. Now, what we need to understand is the classical groups, this represents a set, right? This represents a set of matrices, and those matrices have these properties of preserving the volume and preserving the metric, right? Or one or both, depending on what group we're dealing with. You know, this is the name of a set, right? And the set, the matrices in this set, right? The matrix A, that is an n by n dimensional matrix. And n is the dimensionality of the underlying vector space V, for which these matrices A would act as basis transformations, right? So the idea is, if say we take the special unitary group, you know, PQ, right? That is a set of matrices. If we pull out an element A, I can use that element A to affect a basis transformation on the vector space V, and I know that that basis transformation will preserve the metric. The metric will be preserved. So that's what we're getting at. But this vector space has a dimensionality n, right? And what's about to happen is we're now going to talk about the dimensionality, the dimensions of A, meaning if I pull out a matrix from this group, it has a dimensionality. The problem is that there's a lot of potential confusion here because, yeah, the matrix A is n by n, right? And n is the dimensionality of the underlying vector space. But A is a very specific matrix, right? I can't just put random elements here. Those elements they have very strict relationships with each other, right? This element is related to that element's related to that element. All these elements have relationships that are tuned in just the right ways to preserve whatever metric it's preserving. In this case, the sesquilinear PQ metric, right? So those relationships tie these elements together. So normally a matrix would have n squared independent terms, and if the determinant is 1, for example, then we end up with n squared minus 1, right? We're 1, by demanding that the determinant of A equals 1, for example, we lose the total independence of all the elements, right? So there's now a notion of dimensionality of this matrix that's different than the dimensionality of the underlying vector space. It'll always be n by n dimensional matrix. But the question is how much freedom do we have to choose the individual matrix elements, right? A11, A23, A32, A12, A33, A n and A3 n minus 2, right? All of these are individual matrix elements of the matrix A, which is metric preserving and maybe volume preserving too, or either. And now the question is the number of independent elements to build the matrix A. That is now the dimension that we're interested in, which is a totally different dimension than n, right? It's related to n, but we're now going to wonder is if you preserve a certain metric, how much freedom do you have to create a matrix that does this, right? Because I've not shown you how to make a matrix that preserves, say it was just the Euclidean metric, right? And say it was bilinear. So I'm looking for something where a matrix transform times a matrix still equals the identity matrix, right? So this would be an orthogonal group, 3, 0, right? Because this, if this is true, right? This is the metric that's preserved by the 3, 0 orthogonal group. So now I have to figure out what are these, and this is a 3 by 3, right? What are these 9 matrix elements that do this, right? Now, obviously, this and this are related by the transpose. So just focus on, say, this, right? What are those 9 matrix elements? Well, you may remember what the orthogonal group of 3 dimensions is. But if we want to preserve the volume, we'd be looking at the special orthogonal group 3, 0, which is just written as special orthogonal group 3. You may know how to build that matrix. You probably should, but it has to do with the Euler angles and some other things, right? That's in physicists learn about the Euler angles at one point. But constructing that matrix is not trivial. Certainly constructing it for all the possibilities out there, right? You add a -1 here, now you're scratching your head on how to do it. That's all the representation theory I was going to talk about. The point is that normally you would think, oh, I have 9 independent matrix elements, but that's not true. Once you start squeezing yourself into this requirement to preserve these metric elements, these guys here, these matrix elements are no longer independent. And now the question is how many choices can you make here? So instead of having 9 degrees of freedom, how many degrees of freedom do you actually have? And that's what we'll tackle that a little bit in the next lecture. Okay, so I think we've identified the classical groups. Now we'll talk in the next lecture a little bit about some of their properties, and then we will move on to the next big subject, which is continuous groups and finally Lie groups.